Okay, so here, let's take a look of this function f from z. Z is, it means the integer set to z. Okay, so such that f of, you put an x, you choose an x from the integer set, then it is mapped to x squared in this side. Is that okay? So is this function a one-to-one function? Is it an injection? Injection means it cannot be 2-to-1. It cannot be 3-to-1. So on the right-hand side, one thing on the right-hand side, will there be multiple things on the left-hand side mapped to it? If this is the case, then it is not one-to-one. Is it one-to-one? No, this is not one-to-one. Not one-to-one, you give me an example why it is not one-to-one. Okay, plus or minus 1, they map to the same number, right? Okay, so it is not one-to-one. Okay, but if I change it, okay, so this is a different function. So let's call it function g. This g is, the domain is different. It's a natural number n, and then it is mapped to z. But this time, you have a similar form. Gx is equal to x squared. Then is it a one-to-one? Now this is one-to-one. This is one-to-one. This time, if anything that has the same right-hand side. So if there is two numbers, let's say called gx1 is equal to gx2, then you will have x1, the square of this one must be equal to the square of x2. Am I correct? So this implies what? This implies x1 is equal to plus x2 or minus x2. Am I correct? These are the only two options. But on the other hand, we see that the domain of this function g are natural numbers. They are always non-negative. So one of them has to be rejected. So it means that whenever you have gx1 is equal to gx2, then x1 must be equal to x2. So you cannot have two different things mapping to the same item. So this is a one-to-one function. Okay. Now, proving that it is not one-to-one, you give an example. But proving that this is one-to-one, then you need to have some argument to say that this is the standard way. The standard way is to prove it by contradiction. If there are two things that map to the same item, then you will find something wrong. Is that okay? So we can show things like this. Okay. Now let's try onto. Let's see. Okay. Let's have another function. Let's call it h. This h is from z to z, and then with h of x is equal to 2 times x. Is it onto? Is it onto? Well, no. No. So recall, this is integers. It is integers. Onto, it means that whether the right-hand side here can be completely covered. Okay. Now, the right-hand side here, because it is an integer, x is an integer. So the right-hand side must be 2 times x. It must be an even number, right? So for all the odd numbers, you don't have any correspondence from the first set. Is that okay? So this is not onto. So there is no number x such that, no integer x such that h of x is equal to 1. There's nothing. Okay? So if you look at the set, so this set is what? So the left hand side is 0, 1, 2, 3, 4, and then minus 1, minus 2, blah, blah, blah. The right hand side is also 0, 1, 2, 3, 4, blah, blah, blah. Minus 1, minus 2, blah, blah, blah. Okay? 0 maps to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6, minus 1 maps to minus 2, minus 2 maps to minus 4. Am I correct? So here, this minus 1, this 3, nothing is mapped to it. So the right-hand side is not completely covered. So it is not onto. So this is not onto. Okay? Not onto. But this is 1-to-1. Okay, this is 1-to-1, but not onto. But if I change it a little bit, okay, f, g, h, let's call it function k. Okay, so what is function k? This function k is from real numbers to real number. Then such that k of x is equal to 2x. Is it onto? Is it onto? Yes, this time it is onto. But how can we prove? This one is onto. This one is onto. To show that it is onto, we need to find out the reason why everything here is covered, right? Why? Okay, so the proof is like this. So for every y in R, there exists, let's say, x, which is equal to y over 2 in R, such that k of x is equal to y. Then this is the proof. You give me any y on the right-hand side, I can find somebody, let's call it x on the left-hand side, such that k of x is equal to y. Then in that case, this function will become onto. Is that okay? Okay. So the reason here, so basically what I'm doing here is like this. So this is a real number. This is a real number. You can think of this as a line. So this is 0, this is -1, this is 1. Is that okay? And there's a line here. There's 0, there's a -1, there's a 1. So 0 maps to 0, 1 maps to 2. Is that okay? Okay. And when we want to prove that it is onto, what we are afraid? We are afraid that somebody here is not covered. Am I correct? So let's call it y. But whenever we have a y, which is a real number, then we can always find something called y over 2 on this side. So if y is a real number, y over 2 is also a real number. Am I correct? Is that okay? And it happens that y over 2 will map to y. So in this case, this means that everything here on the right-hand side, no matter what happens, you must be able to find something on the left-hand side to map to it. So in that case, it is an onto function. Okay? Is that okay? Good. Very good. Finally, yeah. 1 onto. So let me use the board over there. So this time, let's say, let me use the board here. Let's call a function, I will use the notation. Let's call it f again. Okay, we use the same f over, we use the same h and k over there. So, because we are using the same h and k. So is it a bijection? And is it a bijection, I'm asking. So is it a bijection? So this is not a bijection. The reason is that it is not onto. If it is not onto, then it is not a bijection. Is that okay? Okay, but how about this one? Is it a bijection? Is it a bijection? So we have already proved that it is onto. So if it is also injection, if it is also a 1-to-1, then it is great. So is it 1-to-1? It looks like 1-to-1, right? Any one thing here maps to one thing here. There's no two things mapped to the same thing here. And how do we prove? Okay, how do we prove? So we have already done that it is onto, and to prove that it is 1-to-1, and to prove that it is 1-to-1, we observe that if there are two values, kx1, it is equal to kx2, then you will have 2x1 is equal to 2x2. Am I correct? And if 2x1 is equal to 2x2, then that means that x1 has to be equal to x2. Is that okay? So whenever they have the same value after the mapping, the original value has to be the same. Okay? If two numbers have the same value after the function mapping, it implies the original value has to be the same, then this is 1 to 1. Because you cannot have two different values mapping to the same value. Okay, so this is not just onto, but it is also 1 to 1. And yeah, this is it. Okay. In fact, there is more than one way to prove a function is a bijection. So we have demonstrated one way to prove that it is 1 to 1 and also onto. You can prove it like it is 1 to 1 from this direction, and it is also 1 to 1 from this direction. Then this is just saying, it is just equivalent to say that there's one thing here mapped to one thing here, and there's one thing here mapped to one thing here only. So then in that case, it is meaning a 1 to 1 correspondence. Is that okay? But we need to be careful. Okay, so to define what is meant by one thing here mapped to this one. Okay, so before we really understand what is going on here, the best way is to prove that it is 1 to 1 and onto separately. So it all so this is the case. Okay, so you have just have an exam, right? So you must be very familiar with counting. So let's do some counting problems. Okay, I'll use the board over there. Okay. Okay, suppose that we have two sets, A and B. So they are sets. We know that they are finite sets such that the size of A is equal to M and the size of B is equal to N. Is that okay? So I have a few questions to ask. So this is the given condition. So the question one is, how many different injections from A to B? Question two is the same. How many different surjections from A to B? And question three is how many different bijections from A to B? Okay? Okay, so how many different injections? How many different? Okay, let's do. Okay, it turns out that the most complicated question is Q2. Let's leave it aside at the moment. The easiest one is Q3. So Q3 asks for how many bijections are there from A to B. Okay, I will tell you. If M is not equal to N, no, 0 of them. Because if you want to have a bijection, the size of A has to be equal to the size of B, because it is a 1 to 1 correspondence. Am I correct? So if M and N, they are different, then 0. There is no bijection. Okay. Else, how many bijections are there? No bijection exists. How many bijections are there? So let's say that A has 4 things, B has 4 things, right? So one possible bijection is this one mapped to this one, this one mapped to this one, this one mapped to this one, this one mapped to this one. Am I correct? There can be other bijection, maybe. The other bijection may be this one mapped to this one, this one mapped to this one, this one mapped to this one, this one mapped to this one. Is that okay? So there are all kinds of bijections. How many are there? How many are there? So bijection, you can think of, okay, let me ask. If you know the answer, could you please raise your hand? Don't be shy, don't be shy. Good. Okay, good. How to think, okay. So bijection is like, you need to find something on the right-hand side to associate to this. It may be the first item, it may be the second item, or the third item, okay. So in the white example, you can think of this as, you are assigning the first item to this one, the second item to this one, the third item to this one, the fourth item to this one. Is that okay? So this is about the white, the first example. But for the orange one, you are assigning 1 to this one, 2 to this one, 4 to this one, and 3 to this one. Am I correct? Is that okay? Now, because it is a bijection, the labels here are always different. You cannot have 1, 1, 3, 4 or 1, 2, 1, 1, something like this. They are always different. So you will find one of them is 1, one of them is 2, one of them is 3, and one of them is 4. Am I correct? Is that okay? Okay, if you understand what I'm talking about and now know how to count the number of bijections, could you please raise your hand? Very good. Okay, so the number of bijections turn out to be equal to n factorial or m factorial bijections. Is that okay? Because each bijection, you can use a permutation of these m numbers to represent it. So there are n factorial of them. Okay, bijections easiest. Okay, so how about the next one? The next question, how about injection? So injection, you need to have a distinct shot for everyone, right? So for Q1, I can also say something about it. If m is greater than, it's greater than n. If m is greater than n, then no injections exist. Why? Injection is, you need to find a distinct place for every new shot, right? So if you want to make m shots, and there are just n different places, and then n is fewer than, n is smaller than m. So you have more shots than the places that you can have. Then what does it mean? It means that there must be some place you have to receive 2 or more shots, right? Is that okay? This is the what kind of theorem tell us this is the case? You have more place. You have more shots than the place that you can have, then there will be some place with 2 or more shots. What is the theorem? Oh, excellent. Yeah, very good. So this is by the pigeonhole principle. Okay, very good. Okay, so the other case is m. So m has to be less than or equal to n. Okay. So of course we have the special case understood. If m and n they are the same, then the injection becomes onto, so it will be m factorial. But how about not? So in general, let's say there are more places. So there are just m people here. Is that okay? And there can be a lot of things here. Okay, so for instance, you can choose, so this is 1, 2, 3, 4, 5. Maybe this one choose 1, this one choose 2, this one choose 3, this one choose 4. This is one way. Okay. Or maybe this one choose 1, this one choose 2, this one choose 3, this one choose 5. This can be another way, right? Right? So how many ways are there? How many ways are there? Okay. How many ways are there? So we can use rule of product to help us to analyze this. So for this one, how many choices are there? So you can choose 1, 2, 3, 4, 5, whatever you can do, right? Okay, so let's make it 6, okay, to easier understand. Okay, so let's say there are 4 things here, but there are 6 things here. Okay. Okay. So this one has 6 choices. this one, because it can choose 1, 2, 3, 4, 5. But then this one has how many choice? If this one has already chosen, this one has how many remaining choice? 5. You don't have 6 choice anymore, because it is an injection. You have to choose something that is not chosen before, right? Okay, so there are now 5 choices here for this one. There are now 4 choices here, and there are now 3 choices here. So for this example, so in this example, m is equal to what? M is equal to 4, n is equal to 6. So the number of injection is equal to 6 times 5 times 4 times 3. Is that okay? In general, how many injections are there? There are how many? There are n for the first choice, n minus 1 for the second choice, n minus 2 for the third choice, and so on and so forth. And then we need to make how many choices are there? We need to make m of them. So there are m terms here. Okay, and this is exactly the number of permutation. You can have n items to pick, but then you pick only m of them. Is that okay? So this is like this. Okay, or if you like, then this is going to be what? Is it PNM? Yeah, I think so, right? So this is like m factorial, because you have m terms. You don't have the remaining m minus m terms. So it is like something like this. Okay. Okay, so this is Q1. Question 1. Now surjection, super hard. Super hard. Surjection. Surjection is what? Okay, surjection, I do the easy part for you. Surjection, so this is Q2. So surjection is so I'm claiming that if m is less than n, then no surjection exists. Okay. So surjection is what? Surjection, you need to cover all the floor. Okay. If you do not have enough item from A, then you cannot cover all the things in B. Am I correct? Because one thing from A covers one thing from B in B. If you do not have enough items in A, then you cannot cover all the items in B, right? Right? So in that case, if the size of A is smaller than the size of B, okay, strictly smaller, then you cannot cover. Okay, else. This is a difficult problem, okay? We don't have time today. Yeah, we are about to, we are about to end the class soon. So I'll let you to think about it at home. So this is difficult. Try to think about smaller cases first, okay? So when there are, let's say A has 3 items, B has 3 items, what will happen? When A has 4 items, B has 3 items, what will happen? So we will look at the case where m is greater than or equal to n only, and then you tell me. So we will talk about this next Monday. Okay, so let's end the class now. Okay, thanks a lot.